All right, guys, so here's the first part of your notes for 3.1. I intentionally meant to do it at the end of the chapter 2, the limit stuff, but we're going to do it now. So example 1, it says find the average rate of change of this function over the interval from 1 to 3. So what you're doing with this is just exactly what you did on your limits test. When you find an average rate of change, whenever you see this phrase, average rate of change, think slope. The two phrases, they're exactly the same. Average rate of change, slope, totally interchangeable. So when you're looking for that, you want to set up essentially a slope formula, like change in f of x over change in x. So you want to do f of 3 and then minus f of 1 all over 3 minus 1. That's all you're doing every time that you're doing an average rate of change formula. So we plug the 3 into the function, we plug the 1 into the function. So when you plug 3 in, you've got 3 cubed minus 3 is 27 minus 3, which is 24, and then minus f of 1, so you've got 1 cubed minus 1, so 1 minus 1, of course, is 0, and then over 3 minus 1, which is 2, so this ends up being 12. Now, a lot of times there will be like a context given, like there is for the next example. If there is, then you definitely need to include units. So for the next one, like I said, this one does have units. So we're trying to compute the average rate of change for this one over the time interval from 23 to 45. So this one, rather than looking at a function, you've got a graph right in front of you. So you're still doing the exact same thing. We've got this point right here, and that we labeled that point Q, and that is at 45, which is time in days, there are 340 flies. I don't know what this problem is, nor do I really want to, because apparently there's a bunch of flies just growing rampant. But on the 23rd day, there were 150 flies. So we're trying to figure out, on average, how many flies were added per day, which is gross. So we set up basically just a change in y over change in x when you're trying to find the average rate of change. So 340 was the second y value, and then minus 150, which is the first y value, and then over a change in x, which is 45 minus 23. So we set that up, so we subtract the numerator, we end up with 190, and then over you subtract the denominator and you get 22. So now this, you do want to divide, so you'd use a calculator to do that, and when you divide you get approximately 8.6. Let me get an exact. Let me grab a calculator. So we divide this, you get 190 divided by 22. There we go. Okay, so we get about 8.636. Because remember, in AP, we do always want to round to 3 decimal places. The book says, or I'm sorry, the picture says approximately 9. Which, of course, if you're going with whole numbers, because you're not going to add 8.6 flies per day. And you always want units, even if they're gross units. So that would be your final answer. Be careful. I mean, depending on what they ask you for, there are certain AP problems that will ask you to round to the nearest whole number, especially in cases like this where it makes more sense to talk about a whole fly rather than, you know, hundredths and thousands of flies. So right below, so we can think of average rate of change as, we're going to say, the slope of a secant line. Which is exactly what we've got going on right here. Slope of a secant line, that's the slope that goes between 2 points. Those are like your classic Algebra 1 problems where it's like, find the line that goes through this point and this point. You just do your classic change in y over change in x, set up a slope formula. So whenever we're talking about the average, we're talking about the slope of a secant line. So average is something that we're more than capable of doing with what we know from algebra, what we know from pre-calc, things like that. But if we move down to the next one, it says, what if we wanted to know the rate of change at t equals 23. So whenever we're talking about at, we're talking about instantaneous rates of change. So I've got this nice little picture for you. And there's a whole bunch of lines, and it looks like kind of a bunch of madness. If you look at like this line right here, this is the original line that we have up on the picture above, and that's the one that goes from 23 to 45 and does like the nice little secant line between there. You can see this arrow up here. What it's doing is instead of being at 45, they're moving to 40. Instead of 40, they're moving to 30. Instead of 35, they're moving to 30. And then you just get closer and closer to 23. So the main idea is the closer you get to 23 and looking at an average rate of change, the closer you get to finding out what the instantaneous rate of change is at 23. Of course, you could go from like 23 to 23.0001, but that's the main idea, is as this point approaches this original point, you'll end up getting closer and closer to what a tangent line looks like, which is this darkest graph right here. is what they're approximating the tangent line to be, which just skims the graph at that one point. It doesn't go through another point on the graph in order to get the slope. So what you're going to write here is as Q approaches P, so as this second point right here gets closer and closer to the original point along the curve, the secant line PQ, which is this line right here. So like from here to here, this is the original PQ that we were talking about up in the problem up above. The secant line PQ approaches the tangent line AB. So you can see we've got B right here and then A down here. So AB is again a tangent line. A tangent line is a line that just goes through one point and it matches the slope of that one point, which is different from a secant line, which always has to go through 2 points. All right, so next one, example 3. Find the slope of the parabola y equals x squared at the point 2, 4. So that's an ordered pair. Like when you plug in 2 for x, you get 4 for y. So write an equation for the tangent to the parabola at this point. So what we need, and I'm going to draw you like the tiniest little picture over on the side. Don't take up much room with this. So we've got a parabola. Looks something like this. Let's say that like right here. Let's say that's the point 2, 4. What we're trying to find is a tangent line to that point, meaning we want to try to like figure out exactly what the slope is right at that one point without using any other points around it. And then if we do that, we'd have what's called a tangent line because it only goes through one point. So that's the goal. So to get a tangent line, we're going to go from 2 to 2 point h, or 2 plus h, I'm sorry. So a secant line, and we've kind of done this already. Okay, so we're going to go from 2 to 2 plus h, and the whole point here is that h is very, very, very small. So we could go from 2 to 2.1, or we could go from 2 to 2.01, to 2.001, 2.0001. So that plus h, that's the little addition of like the 0.1 or the 0.01, 0.001. We're trying to get that value of h. I just realized that looks like it says his. I mean, h is. We want that value of h to be as small as it can possibly be. So when we set up a secant line, we're looking for the slope of that secant line. So we're going to set up a nice little formula, slope formula, just like we did up above. So it's going to be change in y, which is given by this, whatever the function value is at 2 plus h, minus whatever the function value is at 2, and then over 2 plus h minus 2. So again, we've seen something like this before. So what we do is we plug this, whenever you have f of whatever, you plug it into the function and then kind of simplify it down. So our function is y equals x squared. So we're going to plug the 2 plus h into x squared, and then minus, then we're going to plug the 2 into the x squared. We're going to simplify that whole numerator down. And then what happens down here is the positive 2 minus 2 cancels each other out. All we have left is that h. So in the numerator, the 2 plus h gets squared. That means you do 2 plus h times 2 plus h. It does not mean you square the 2 and you square the h. Please don't get caught up in that. So 2 plus h times 2 plus h, picture you're doing some invisible foiling, and you end up with 4 plus 4h plus h squared. And then you subtract a 2 squared, which of course is 4. So we're just working on all of this algebraic simplification that we need to do. So just like the denominator down here, over here, the positive 4 and negative 4 will cancel each other out. And then you'll notice that this term has an h, this term has an h, so we can reduce everything down by h. So we end up with a 4 plus h. So what this says is that the slope between 2 and 2 plus h, whatever h is just given as 4 plus h. So if I went from 2 to 2.1, the slope would be 4.1. If I went from 2 to 2.01, the slope would be 0.01, because here my little h was 0.01. If I went from 2 to 2.001, this would be 4.001. So the whole point is I want that value of h to get smaller and smaller and smaller. So as h approaches 0, which is what I want to happen, I want it to go from 0.1 to 0.01, 0.000001, we would like that distance to shrink down to 0, because that would mean that we're just looking at one point on the graph rather than 2. So as h goes to 0, 4 plus h goes to 4. So what that means is that the slope of y equals x squared at the point x equals 2 is 4. And you can kind of see that. I mean, when you're looking at a graph, especially if you literally plotted it on a calculator, it's definitely got a positive slope there. And as you move from this point, kind of move along the curve, it's definitely getting steeper. The farther you go, the steeper it's going to get. So that's a slope. What they want is a tangent line. So the tangent line, we did stuff like this. We're finding a line that goes through this point and has this slope. So we did stuff in point slope form before. We do y minus the y value, which they gave to us, was 4, and then equals the value of the slope, which is 4, and then in parentheses, x minus the x value, which is 2. We talked about this at the beginning of the year. On my test, on the AP test, whatever, there was no need to simplify that down at all. You can just leave it in point slope form, just like that. All right, so we've got another example here. So we're trying to find another slope. Here's another fun little equation. This time we're trying to find the slope of the curve at x equals a. So just like a generic value of a that we're not going to specify yet. So when we're trying to find a slope, we want to find the slope between a and a plus h, which is just the teeniest little bit above a. And we're going to try to take that value of h and shrink it down to 0. So the slope, we start with f of a plus h, and then minus f of a over a plus h minus a. So this is just a run-of-the-mill slope formula. Change in y over change in x. I plug it into my original function right here, and I can start to simplify down. So this is going to be 1 over a plus h, and then minus 1 over a. This is, again, just over h, because the a and the negative a will cancel each other out. So up here in the numerator, I need to get a common denominator between those two, so with the a plus h and the a. So here I multiply by a over a. Here I'm going to multiply by a plus h over a plus h. So when we continue to simplify down here, this is going to be an a over a times a plus h, and then minus a plus h over a times a plus h. So I'm in the process of getting that down to just at least having the numerator with just one piece, and then I can divide by the h. So this equals, if I simplify this down, I'm going to have a common denominator of a times a plus h, and then in the numerator I'm doing a minus the quantity, a plus h. So the a's will cancel, but then be really careful here because I'm still subtracting the h. So I'll actually have a negative h in the numerator, and then over that h in the denominator. So I'm just about there. I'm going to take this numerator here, and then I'm going to multiply by 1 over h instead of dividing by this h right here. So the h's will cancel. So here's what I'll end up with, is a negative 1 over a times the quantity a plus h. So that's the formula that I get for the slope. So remember, again, I'm trying to see what happens as h approaches 0. So as h approaches 0, now this is just like limits. Your first method should always be direct substitution, and I can just plug the 0 right in here because it doesn't give me a denominator of 0. So the slope approaches negative 1 over, and then a times a plus 0. I can just plug a 0 right in for the h because I'm hoping to go just from a to a, right on top of each other, same point. So this ends up being negative 1 over a squared. So that is a formula for my slope no matter what value of a you choose. So I'm going to put the calculator over just so I can show you guys. So if we look at the graph of 1 over x, and you guys can either follow along or not, whatever. So if we graph this, let me get a, yeah, it's a good standard window. So what this says is that if you pick any value a, so if you pick x equals 1, if you pick x equals 2, if you take a look at this first quadrant, we've graphed this graph so many times, we should know what it looks like. This is a constantly negative slope, no matter what. And it gets really, really steep as I go closer to 0, and then it really levels out. So supposedly, this is the slope at any time. So say I plug in 1, that would be negative 1 over 1 squared, which would be negative 1. If I plugged in 2, that would be negative 1 over 4. If I plugged in 3, That would be negative 1 over 9. So you can see, I mean, that's pretty much what's happening. Even after I get past 1, that slope is pretty much nothing. So you can see that that's going to be a good formula for the slope, no matter what I plug in for a. And then over here, basically the exact same pattern is happening. This slope is always negative as well. The bigger my negative number, the less steep that slope is going to be. And then if I plug in like decimals smaller than 1 or negative 1, it's going to be a really, really steep slope. And another thing to notice, the slope is always negative every little bit of this graph. This formula is always going to spit out a negative number because you've got a negative 1 over a squared, which will be positive no matter what. So this next part, I kind of actually answered while I was going through the graph. I don't know if you caught it. Where does the slope equal negative 1/4? So what we can do is take the formula for our slope and just set it equal to negative 1/4. So it's not too hard to see if we set those equal to each other because the numerators are both a negative 1. If we set a squared equal to 4, we actually come up with 2 answers. We come up with positive 2 or negative 2. So there are 2 different places where the slope will equal negative 1/4. So just to show you guys again, that does in fact give you 2 different values there. If you look, right around here at negative 2, that looks like it could be a slope of negative 1/4. Definitely negative and not very steep at all. And then same thing here at positive 2. Could also be the exact same slope of negative 1/4. And then what happens to the tangent to the curve for different values of a? So one of the things, this is kind of what we were talking about, we want to see what happens kind of as we move throughout that curve. So a couple of the notes that I've been saying. First of all, the slope is always negative. That's one thing to comment on. And then we talked about how as we go off to the right and off to the left, the slope is pretty much just zeroing out. It's getting to be a really, really small number. Always negative, but a really, really small number. So as a, these values of a that we're using for x, as a goes off to either positive or negative infinity, the slope is just basically becoming 0. And then we could do the opposite. As a approaches 0, from the left or from the right, the slope is getting super, super steep. It's actually going to be negative infinity for both of these. So as a approaches 0, the slope is approaching negative infinity. It's always going to be negative, but it's going to be unbelievably steep. Because picture if you plug in something really, really small, like a 0.01 or a 0.001 or something like that, having that teeny tiny number in the denominator approaches negative infinity. That's what we talked about with the tinies for this last unit. So these are just some comments to come up with for different values of a. All right, last little bit here. The normal line, very similar to a tangent line, but it's a perpendicular line. So instead of having the same slope, it's got a perpendicular slope. So this is the line perpendicular to the tangent line. So the last thing we want to do is we want to write an equation for the normal line to the curve. So if we talk about the normal to the curve or the tangent to the curve, we're talking about basically a similar idea, except if you compare them to each other, their slopes would be opposite reciprocals because they're perpendicular to each other. So if we want at x equals 1, remember we look between 1 and then like a little 1 plus h. And we want to take that h and we want to shrink it down to 0 so that we're basically just at 1, like from 1 to 1.00001 or something like that. So I set up the slope just the way I did in those last couple examples. So f of 1 plus h, which could go from 1.1 to 1.0000, 20 zeros and then a 1, minus f of 1, and then over 1 plus h, minus 1. So just like it has every single time, and it will every single time, those numbers are going to cancel out. Then I'm going to plug the 1 plus h into my function up here. So I start with 4 and then minus 1 plus h quantity squared, minus, then I want to plug in the 1, 4 minus 1 squared. All of this is just over an h. So this part, this stuff ends up being kind of a lot of algebra. So I want you to look in here. So I've got 4 minus, and make sure you are careful with your parentheses because you're subtracting an entire quantity. So 1 minus, if I take that 1 plus h, write it out twice, FOIL it out, I get 1 plus 2h plus h squared. And then minus 4 minus 1 squared, of course, ends up being 3. Over h, and then it's just some more algebra to get through here. So when I'm subtracting everything, I have 4 minus 1, which is 3, and then minus 2h minus h squared. Don't forget about that. You're subtracting everything in the parentheses here. And then you subtract 3. So what should happen here is any constants that you have left over should cancel because everything should have an h, because then it's going to reduce down with this h here. So I get a negative 2 because the h is reduced down, and then minus h. So that's a formula that represents the slope, and you could plug that right in. Whatever value of h you use, you could plug it right in here, but again, the entire point is to get our value of h to shrink down to 0. So as h shrinks down to 0, the slope, and again, direct substitution works here. If h is 0, the slope is negative 2. So as h heads towards 0, this expression will head right towards negative 2. And again, you can just do that by direct substitution. So just to show you, again, I'm going to plot that 4 minus x squared, just in case any of you are curious. So if we take a look at this graph, just a nice little parabola here. So it's saying that at the point x equals 1, which is right around there, it's saying that the slope is a negative 2, which seems about right. I mean, definitely negative. And you guys will get better at gauging whether it looks like, you know, a slope of 1/2 or a slope of 3 or whatever, but we can at least be confident that it's definitely a negative slope. So what we're trying to do now is we're finding something just like a tangent line, except we want the slope to be perpendicular. So a perpendicular slope, sorry, that was supposed to be a little perpendicular symbol, and it wasn't a very good one. The perpendicular slope would be a positive 1 over 2. If the original slope was negative 2 over 1, technically, the perpendicular slope would be positive 1 over 2. So the next thing we need, let me write down this is like our generic point slope form here. We were given the x value, so we know that's 1. And then the slope that we're using for the normal line is 1/2. We still need this y value. So the y value is the very same y value that's on this original function. So the y value, we need to find f of 1. And we just plug that in right here. So 4 minus 1 squared just ends up being 3. So y minus 3, whoops, that would be equals, y minus 3 equals, the value of the slope is 1/2, and then we have x minus 1. So that would be a normal line. So just really quickly again, let me show you what the normal line would look like. So to get the y by itself, just add 3. So 1/2, and then times the quantity, whoops, shouldn't have deleted the original. There we go. So 1/2, and then times the quantity x minus 1, and then you would again just add the 3 over to get y by itself. So here's the normal line. So what the normal line does is it runs right through that point, but instead of running like right with the slope, it runs perpendicular to the slope. So let me show you the tangent line as well. So I'll plug in that very same line, but with my original slope of negative 2. So this is what the tangent line looks like. So you can see that it hits the point, hits the graph, the original parabola when x equals 1, and it takes on the exact same slope as my line has at that one particular point. And then what the normal line does is it runs perpendicular to the tangent line, but through the very same point. So, and then your screen gets morphed because it's not a perfect square, so I know those obviously don't look perpendicular, but that's because each one on the x-axis is much wider than each one on the, each one on the x-axis is much wider than each one on the y-axis. So don't worry about the fact that it doesn't literally look perpendicular. So that's it. We'll work on some problems tomorrow.